Everybody? Here we go. Anything else? All right, so let's just do the quiz because it shouldn't take us too long. How was that? That was designed. That was supposed to be a free quiz, like a chance for you to get a really easy, quick grade if you understand what's going on, right, in the class. So the first one, if you ever see 0 over a non-zero number, so the bottom is like saying 0 over a fixed number. What happens? You get 0, okay? All the time, every time, right? If you see 0 over 0, you gotta do some algebra, some sort of trick, right? If you see non-zero or a fixed number over 0, that's what we did at the end of last class. You're either gonna get infinity, negative infinity, or does not exist. Now, this limit, there was no work to be done. You should recognize this as being the limit of sine of junk over junk. The junk matches exactly, these match. And as you let x go to 4, these both go to 0. So the answer is 1. That's it. All right? So there's no work there. All right. If y'all are just coming in, y'all missed a quiz. So please be on time. Where are we? All right, so we're going to continue 1.6, all right, 1.6 or 1-6. I'm going to pass around the sign-in sheet as well. We're going to continue, right, this idea from last class. There were no questions over homework or anything? Yes? 55. Is that one challenging one? See me after class if you want to talk about it, or before class or during office hours. I don't want to do that one. I want people to have a chance to really think about it. So, are there any other ones? Let me double check that that's the one we're talking about here. You said 55? Yeah, let's hold off on that. I can give you some hints to maybe help you. All right. All right. So this idea of limits involving infinity, what we talked about last class is that if you ever see this, right? If you take a limit, and it doesn't matter what you're doing, right? What limit is what's approaching what? That doesn't matter. Doesn't matter what you're taking the limit of. If you get from this limit a fixed number over 0, first of all, you know that there's a vertical asymptote there, right? So that means that your function's going to be doing both sides up, both sides down, or maybe like that or like that. So that's the first thing. You know that there's a vertical asymptote there. So the notes talk about, okay, this tells you there's a vertical asymptote there. That's what all these notes are about. Now, in terms of the limit and an answer, there are only 3 possible answers. Infinity, negative infinity, or does not exist. So let's do another example, all right? Let's do another one of these so that we can make sure that we're somewhat comfortable with them. Maybe we'll do 2 before we move on to the next topic. So how about this one? Limit x approaches, let's go to -4. And let's do something like x minus x squared over 4 plus x squared. So first thing with all limits, right, is to check to see that you've got something going on, like a problem, right? So we plug in. On the top we get -4 minus -4 squared. On the bottom we get, 4 plus -4, but then all of that squared. What's the top turn into? This is -4 minus, that's 16, right, when you square the negative? So negative 4 take away 16 is negative 20. Yeah? So you get negative 20 on top. And on the bottom you've got, that's going to 0, right? So we have the situation where you have a fixed number on top, right? Fixed non-zero number over 0. In fact, we know that the top is a fixed negative number, so I'm put a little negative up there. Right? That's what we know. So I know there's an asymptote here. Like if you were to graph this as a function, I know there's an asymptote at negative 4. Right? If I drew it at negative 4, I know I have a vertical asymptote. What I don't know is what's happening as I approach 4. Both sides are either going up or they're both going down, or, like I said, it could be different on each side. Which side am I asking you to check from here? Is that left? Careful. Both. Remember, the negative here is the negative 4, right? I didn't put the negative up top. So just be careful. That's the reason I like to do examples like this in class, just to make that distinction so that we don't accidentally treat that negative as coming from the left. All right, so we have to check both sides, don't we? We have to check both sides. So I'm gonna sit here and I'm gonna start first by checking the left, coming in from the left. So I'm gonna check from both sides. So I'm gonna do the limit. Let's check from the left first. So I'm gonna do limit x approaches negative 4 from the left of x minus x squared over 4 plus x, that quantity squared. So what did I do here last class when I was doing these problems? What was the next step? Go ahead. Yeah. Yeah, so I was going to go, I drew a number line, didn't I? I drew a number line, and I said, hey, I'm going to look at negative 4, and I'm going to come in from the left side, and I'm going to imagine picking a point to the left of negative 4 and seeing what would happen if I plug that in here. Remember, all I care about right now, is that this is a fixed negative number. All I care about is wondering if this right here is a positive or a negative number. Is the bottom really small or the bottom really big? Yes?
Do we have to figure that part out since the bottom is square? Doesn't it have to be positive?
That's correct, yes. So you're seeing that. That's good. I'm gonna allude to that in a second.
Oh.
Yeah, but you're seeing it, exactly. So let's follow the procedure that I gave you, which is to do this, right? Think of a number to the left of this, which would be, careful, negative 4.01. And then you take that number and you imagine plugging it in right there. So what would happen if I plugged it in right there? 4 plus negative 4.01. That would be a positive or a negative number? Take 4, take away a number that's a little bit bigger than it. It would be negative, wouldn't it? This would be a negative number. Yes? So that's what you would get in here, right? But what's being pointed out is that, wait, does that even matter? Does it even matter that this is going to be a negative? We're going to wind up doing what with it down there? Squaring it, right? So isn't that going to become positive, regardless of what it was, right? So it really actually doesn't matter which side I come in from, right? No matter which side I come in from, whatever this is, positive or negative, when I square it, it becomes positive. So the denominator will always be a small positive number. Understand? Now, we could have seen at the very beginning and just done the answer, right? And just said, okay, it's always positive because it's squared down there, but I wanted everyone to see, just like we're going to follow the procedure, but now we recognize that that's squared, so it doesn't matter. It's always a positive down here. So that means I always have a positive. Do y'all see I don't have to check from the other side? That's the main idea here. I do not need to check from the other side because it's going to be squared, and so it's not going to matter what happens. What's my final answer, though? Negative infinity, right? Because the top is negative 20. The bottom is headed to 0 through really, really small, right? It's headed to 0, but through negative numbers. Positive numbers. So the ratio of a negative divided by a positive is negative infinity. Who has a question? I'm seeing some looks on faces here. You all right? If this was cubed, not squared, cubed, would you be able to conclude the same thing? No, because cubed doesn't always turn out to be positive, so you'd have to check from both sides. Yes?
On a printout sheet that has like the guide of
Mm-hmm.
fixed on facts will show us if we're going to choose the negative infinity or positive infinity.
It shows it on there.
Uh-huh.
Yeah, it does. But I mean, just think about it. It's a negative divided by a positive, right? Negative divided by positive is negative. All right, let's do another one. Limit x approaches 0 from the left of x plus 1 over sine x. All right, we have not had one like this. The difference here is that I'm giving you a problem that has a trig function in it, right? As opposed to just like polynomial stuff or rational function. So let's check to see what happens, right? Let x go to 0. We're coming in from the left. X go to 0. The top heads to where? 1, right? The bottom is headed to? Well, sine of 0, 0, right? Sine of 0, 0. So we get 1 over 0. That's a fixed positive number over 0. So what I need to determine is whether or not that 0 is positive or negative, right? Like, is it headed to 0 through little positive numbers or little negative numbers? So normally what I've been doing is I've been drawing a number line, I've been putting 0 here, and we've been coming in from the left, right? Okay, let's do that. Let's take a number to the left of 0. What do you want? Okay, thank you. Negative 0.01, right? It's a little negative number there. Negative 0.01 is a number to the left of 0. Yeah? Are y'all okay? Yes, yes, okay. All right, and then what am I doing with this number? Plugging it into the denominator right here for x. So now you need to know what sine of that is. Right? So I know you're going to want to go grab your calculator. Don't grab your calculator because you took pre-cal, and so you understand what the sine function looks like, don't you? Like, you know what the graph of sine is. So I'm looking at this denominator, and instead of trying to plug in that number in there, I'm just going to think about the sine function. Looks like this, right? And then if I go backwards, it looks like that. And what I'm doing is I'm asking you, what does this sine function do as you approach 0 from the left? So look at the sine function and approach 0 from the left. Where's it headed? Here's 0, right? Approach 0 from the left. You're down here, aren't you? Coming up. What are you approaching? 0. So we knew that, right? We were approaching 0. But are you approaching 0 through positive numbers or negative numbers? Negative, right? Because you're below the x-axis, right? So you know you're going to have little tiny negative numbers. So this is going to be negative. And now again, the ratio of a positive over negative is negative. So you get negative infinity. Is that clear? There's another way you could have done that without the graph of sine. I'll show it to you just in case, you know, some people think of things differently. So another way you could do it is go back to the unit circle. And remember that if you're at any point on this circle, if that's the angle theta, the x-coordinate is cosine theta, the y-coordinate is sine theta. Right? This is like one big takeaway from pre-cal. The x-coordinate is cosine, the y-coordinate is sine. So if I ask you to take a tiny negative number and plug it into sine, that means that little negative number is the angle, right, that we're plugging in. And so I'm asking you to plug in a tiny little negative angle. So here's 0. A tiny negative angle would rotate you down a little bit, right? Just down. So if I'm down here, just a little bit like this, and I want to know what sine is there, right? Sine is the y coordinate. That would be positive or negative. I'd be negative there, right? That's a negative number, that's a positive number, because I'm in the fourth quadrant. So that would tell you that, hey, yeah, I'm approaching 0, but I'm a little tiny negative number. So either way, you look at it. What I don't think you should do is take that and get your calculator out and plug it in, because that you're not using what you know about these functions, and the whole reason you kind of took pre-cal is to get some grasp on these functions. Questions? All right? All right. Let me see, make sure I didn't miss anything here. Please read through these notes yourself in terms of the whole idea about vertical asymptotes. I've already verbally explained the idea, but read through this. And if anything doesn't make sense, let me know. Let me see. All right. All right, so everything we've been doing, when we started this section, everything we've been doing are called limits at infinity. So what that meant is that when we did the limit, we were getting infinity as an answer, right? Or negative infinity. And then maybe sometimes does not exist, but infinity or infinity was the answer. And so those are called limits at infinity. We are now going to transition to a different type of limit. Oh, you know what I forgot? Hold on a second. I forgot this one. I apologize. This is my fault. This is a property that we need. Pause, time out. I forgot to give you this. These two properties here are going to be extremely useful for us in a little while. So, well, you know what? I can wait. Let's do this. Look at that picture right there. This is the graph of f of x is 1 over x, all right? That's the graph of f of x is 1 over x. My first question to you is just by looking at the graph, what is the limit as x approaches 0 from the right? Approach 0 from the right. What's your answer? Positive infinity, right? So approach 0 from the right, you go to positive infinity. 0 from the left, negative infinity. What's the limit as x approaches 0? Does not exist, because if I say 0, I'm saying approach from left and right, and those don't match, right? Okay, that is what we've been doing, right? Now I'm going to ask you a different question. What happens to this function as I start going out to the right further and further and further? What is the graph of the function doing? Or what is the function doing? It's getting closer to 0, right? So the bigger x gets, right, the larger x gets, the smaller the function gets, right? How about this direction? The bigger x gets in the negative direction, the smaller the graph gets, yes? This is a new type of limit that we have not talked about. It's called a limit at infinity. So notice this notation, limit x goes to infinity. We've not had this yet, right? X has always gone to a number, hasn't it? X goes to 2, x goes to negative 5, x goes to 0, right? We've never had x go to infinity. That's what this is about, this next topic. So let me write the notation down. If you see the limit, you see x approaches and you put infinity like this of some function. What this is basically asking you to do is to find the, what we call right end behavior of the function f. We're trying to find the right end behavior of the function. We're trying to say, hey, look, as x goes out further and further to the right, what's the function doing, right? Now, if you change that and you do the limit as x goes to negative infinity of the function, now you want the what? Left end behavior, right? I'm not going to rewrite all that. I'm just going to put this. This is asking for the left end behavior. So what we're doing is we're trying to imagine what happens when we let x grow without bound. That's the way math people like to say it. We're letting x grow without bound. It just keeps getting bigger and bigger and bigger, and what happens to the function? So let's look at our first example that I already showed you the picture of. Let's look at that function f of x equals 1 over x, right? So if I take this limit, I let x get huge, right, go to infinity, of that function 1 over x. What did the graph say was happening? That's the same graph we looked at just a second ago, right? It looked like this. It approached 0, didn't it? So as you go to the right, that graph was getting asymptotically up closer to 0. In college algebra, we called that a what kind of asymptote when you go towards it on the ends? These are vertical asymptotes, right? Horizontal asymptotes, right? So this thing is headed towards 0. Do you all believe that? From the picture, do you all believe that this is headed towards 0? Yeah? But can you convince yourself from this right here? Think about what's happening here. Up top, you have a fixed number, don't you? In this case, it's positive, right? And then you're dividing that by a number, right, x, and where's that number headed? To infinity, right? Not to 0 this time, to infinity, right? So imagine you have a number on top, the number 1, and you start dividing it by bigger and bigger numbers. What happens? That ratio gets bigger or smaller? It's smaller, right? Imagine 1 divided by 10 would be 1/10. 1 divided by 100 would be 1/100th, right? 1 divided by 1,000,000, 1/1,000,000th, really small, right? So I want you to understand this more like you have a fixed number over a number that gets large, that ratio goes to 0. That ratio gets small. Now, would it have mattered? Would it have mattered if this was a negative number on top? What do you think? Same answer? If that's a negative number on top, a negative divided by a huge number would be a very small negative number, but it would still be headed to 0, wouldn't it? So this it turns out, and you can see this in your limit summary, that page I gave you at the very beginning of the semester with the boxes. I believe this is the bottom right-hand corner. It's the bottom right-hand? Yeah. Let me look at it real quick. Yeah, so if you look at the bottom right-hand corner of the limit summary, we are looking at that bottom right case. From here on out, anytime we take a limit and you have fixed over fixed, and it doesn't matter if it's positive or negative, over something that's becoming infinitely big, that ratio will always go to 0 every single time, all right? So what about this? Let's try another example. Let me just do a limit. I'm not going to write the function down. What if I ask you for the limit as x goes to infinity of 1 over x squared? I want to just stop for a second. Do y'all see how calculus is, so far, is not really like algebra or pre-cal in the sense that we're not trying to, we're talking about the way things behave, right? We're looking at, what happens as things get close to something, right? As things get bigger. We're not saying what happens at 2, right? It's a very different, more abstract way of thinking about things, right? So here, I want to let x go to infinity. So I can't plug infinity in because infinity is not a number, right? It's an idea. So what happens if I take a number that's getting bigger and bigger and bigger and plug it in here? Well, the top is fixed, right? The top is fixed, and it's positive, over Now on the bottom, what's happening? Well, infinity, right? It's getting huge, and then we're squaring it. What happens when you square something? It usually gets bigger, right? Can you ever square anything and it gets smaller? What do you think?
Something that's less than 1.
Less than 1. So if you take a fraction like 1/2 and square it, what do you get? It's 1/2 times 1/2. 1/4, which is smaller than a half. Right? So there are certain numbers that if you square them, they get smaller. But there are numbers where their absolute values are less than 1. But generally speaking, if you're outside of 1, numbers, you square them, you get bigger, right? So is this a real small number close to 1 or less than 1? No, right? X is going to infinity, that's a huge number. You square a huge number, it's going to be a huge number. So really the bottom is like still infinite, isn't it? It's still kind of infinite. So what happens when you have a fixed number over a number that gets bigger? The ratio gets smaller, right? And this goes to 0. And there's no work, okay? There's nothing I have to do here. There's nothing I have to do. I just have to recognize that I have a fixed number over infinity, and I'm done. The answer is 0. So that brings me to the property that I was going to show you. Where is it? This property that says that if you do the limit as x goes to infinity of 1 over x, as long as the power on x is a positive integer. So if it's 1 over x, or 1 over x squared, or 1 over x cubed, or 1 over x to the 4th, as long as this is a positive integer, then your answer is going to be 0. Do y'all buy that? I mean, I did it for 1 over x squared, right? But what if this was 1 over x cubed? Same idea, right? You're cubing infinity, it's still going to be huge, right? And also, it wouldn't matter if you go to negative infinity as well, because you have a fixed number over something that gets big, and that will always go to 0. So just know of this property. I'm going to use it, so you'll get used to it. I'm ready for another example. Things are about to get not so fun. You ready? How about this? Limit x goes to infinity. Let's start easy here. 4x plus 1 over x minus 3. Let x go to infinity. Let x get bigger and bigger. We can't plug infinity as a number, right? But the idea here is that it gets larger. So what is 4 times a huge number? Huge number, right? Plus 1? Still a huge number, right? So would you agree that the numerator is headed to infinity? It's just getting bigger and bigger and bigger. Yes? And I'm dividing that by, okay, huge number, right? Take away 3. Still a huge number, right? So the bottom is also getting bigger and bigger and bigger. Yes? So we have infinity over infinity. Have we seen this before? No, right? We have not seen this. What have we seen? 0 over 0, right? That's what we started this whole idea of limits with. That was bad, that was algebra, right? Then we did, well, 0 over fixed is just 0. Fixed over 0 is infinity, negative infinity does not exist. And fixed over infinity is 0. Do I need to write those down? They're on your sheet, right? They're all on here. Can I have it again? We have, off this sheet, we have talked about the top right box, the bottom right box, and the bottom left box. We've got all those covered. We have also in the top left box, we have talked about 0 over 0, haven't we? But do you see what's right next to 0 over 0? Infinity over infinity. And what does it say you have to do? Back to the algebra trick, okay? So we are now back to a place where we cannot just look at this and give an answer. Infinity divided by infinity is not 1 because it's an idea. This is a very large number divided by a very large number. What is that? I don't know, right? You don't know, I don't know, because they're not the same numbers. Do you understand? And when I say large, like this could be a billion, right? But this could be like a trillion to the trillionth power, which would be big as well, right? So this is like it's like a tug of war. It's like the numerator's trying to get big, the denominator's also getting big, and they're kind of looking at each other. It's like, who wins, right? Who wins? And so that's our job, is to figure out who wins. Sometimes the numerator will win, sometimes the denominator will win, and sometimes they just kind of like compromise. They say, that's enough, let's just meet in the middle somewhere, right? Every problem is different. So we need a method, we need a procedure, something that we can do every time we see this. So when we saw 0 over 0, it was algebra trick, right? What kind of algebra did we do? Difference of squares, difference of cubes, just factoring in general, right? We also had conjugates. We had, missing something. Oh, combining like fractions together, right? So there's all this algebra that we had when we saw this, right? When we see infinity over infinity, the general rule of thumb, okay, the general rule of thumb is this. And follow me through it first. First time you see it, you'll be like, what? Why am I doing this? But this is the general approach to infinity over infinity. What we do is we look at the denominator and we find the highest power of x that we see. Now in this case, I have x to the first power. So I'm going to focus my attention on this, all right? And then what I'm going to do is on the outside of this fraction out front, I'm going to multiply by 1. And the reason I'm going to multiply by 1 is because if I multiply by 1, it doesn't change anything, right? But the one that I'm going to pick is going to be constructed in a certain way so as to help us get to an answer, all right? So what I'm going to do that, or what I'm going to pick is this. I'm going to put out here on the top and the bottom, it's going to be a 1. Well, let me do it on the next line. I'm just going to rewrite everything. This is going to be a 1. Okay. I'm going to multiply out here on the top and bottom by something that will make that x go away completely. Right? So remember I said we're going to look at that x right there, the highest power of x we see. I want to make x go away. So the only way to make x go away is to divide x by x. Right? X divided by x would be 1, right? So I'm going to put out here 1 over x. And if I do that on the bottom, I'm going to do 1 over x on the top. Do you all agree that that's 1? Yes? Now, again, just follow me through this first example. I know this doesn't seem natural. Let's just go through it, all right? So now what I have to do is distribute the 1 over x through the parentheses. Okay? Both the top and bottom. So now I have this. Limit x goes to infinity. Okay, what happens when I multiply that times that? What's 1 over x times 4x? X's cancel, right?